you want to say something, Dima? I cannot hear you because you're muted.
Yes, I wanted to welcome back everyone after the Passover break. And I wanted to say that we started YouTube broadcast and finally introduce the speaker, Siddhartha Sahi from Rutgers University. He will speak on a reduction principle for Fourier coefficients of automorphic forms. Please.
Thank you, Dima. Thank you for the invitation. And yeah, so what I'm going to speak about is joint work with Dima and first with Raul Gomez and more recently with Henrik Gustafsson and also Axel Kleinschmidt and Daniel Persson. And this paper that I'm going to talk about is sort of the one of the last two papers in some series of papers. Maybe some of you have heard some of these ideas before in talks by Dima or by my collaborators, but I'm going to try to make it, well, I'm going to try to explain the ideas as simply and as non-technically as possible. So that will be my attempt. Okay, so let me start. Okay, so what is our main result? So we establish a reduction principle for periods of an automorphic form and for a reductive algebraic group G, which is defined over a number field K. And if you're not already in automorphic forms, then you might ask, why do we care about these unipotent periods? Well, they're important because sometimes they encode quantities of arithmetic interest. So now unipotent periods just involve a unipotent group and a character, and we focus on some important subclass of such unipotent periods. And because we just work with them, we decided to call them Fourier coefficients. And maybe it's a little bit presumptuous to call just these things Fourier coefficients, but the term has been used elsewhere in the literature for something more specialized. So, okay, then after all, we didn't feel so bad. Okay, let's call these Fourier coefficients. So what are these, what's special about these Fourier coefficients is that they're indexed by a Whittaker pair in the Lie algebra. And this Whittaker pair consists of a semi-simple element in the Lie algebra and also a nilpotent, and they are related, and I'll explain that in a moment, but it's some subclass of unipotent periods. So some special cases of these Fourier coefficients, they have been studied extensively in number theory, and other special cases have been studied more recently in physics. And I'm not a physicist, but beginning to understand a bit more. And they arise in string theory when you're studying non-perturbative effects in some expansion and parameters. Then these some of these Fourier coefficients show up in this calculation, in these calculations. Now, this is almost true, but that in number theory, the main thing is the nilpotent phi, and the S is kind of auxiliary. There's some canonical choice, and you just make that. In string theory, this S is actually a key ingredient, and this phi is almost auxiliary. Again, not quite true, but roughly that's the way it is. I mean, this S is important. It defines a parabolic that you care about. Okay, now in our situation, the flexibility of having this S and the phi together and studying this whole family, it allows us to prove sharper results even for these special cases. That's the reason to look at this class. Okay, very good. All right, so our results are proved in this kind of useful generality when for pair G and gamma. So G is a finite central extension of the Adel group, and gamma is a discrete subgroup of G, which maps isomorphically onto the group of K points. So K is a number field, and okay. So in other words, we're assuming that the covering splits over G of K, and we choose and fix a splitting, and therefore we just yeah. So that's what gamma means. That's what G means, and that's what gamma means. And this okay. So this setting includes these extensions that were studied by Berlinski and Deligne, K2 extensions. So this is true in this situation. Also, if I'm in this setting, then the covering map, this finite cover, it has a canonical splitting over unipotent subgroups. And so I can just think of them as subgroups of G. Very good. All right, so now suppose I have eta, it's just, okay, for the moment, just a left gamma invariant function on G. And chi is a character of n, which is trivial on n intersect gamma. Then I can define the n chi unipotent period of this eta by this integral. N chi, u sub n chi of eta is the function in G, which is given by this averaging with respect to the character. Again, this bracket notation just means this coset. You don't want to, yeah. Oops. Okay, so this quotient is compact, so this integral will converge under fairly mild conditions in eta. So it's a well-defined integral. Now, if the n and the chi, they come from a Whittaker pair, S and phi, then one can actually say more. So one can say more about this period. All right, so what is this Whittaker pair? Well, so first, if I have an element in the Lie algebra G, I say this element is Q semisimple. If S is diagonalizable, the adjoint action is diagonalizable, and the eigenvalues are in Q. Okay, so then I'm going to write G as lambda for the lambda eigenspace. So G is, yeah. G is the Lie algebra. Okay, then I'm going to write G as lambda for the lambda eigenspace, and I'm also going to introduce such notation G as sub greater than lambda, G as sub greater than equal to lambda, and this should be pretty self-explanatory. Right? It's just the sum of eigenvalues bigger than this. I mean, this makes sense if your element is Q semisimple. We can talk about these things. Okay, and we use a similar notation for G star. Okay, now if I have a pair S comma phi in G cross G star, then I say this is a Whittaker pair if S is Q semisimple and phi belongs to the -2 eigenspace for S acting on G star. Very good. All right. Now I write G sub phi for the stabilizer of phi in the Lie algebra, and I set NS phi to be okay. So I take the eigenvalues bigger than 1, and among the eigenvalues equal to 1, I take the stabilizer of phi. And I call this NS phi. And okay, so with this choice of phi, with this choice of NS phi, my G star, my phi, little phi, is actually a character of, so NS phi is a nilpotent Lie algebra, and phi is a character of this nilpotent Lie algebra. And so by exponentiating, I am going to get a unipotent subgroup, capital NS phi, contained in G, and a unitary character, chi S phi, of this group, because this is what I did at the Lie algebra level, and I exponentiated. And then we define Fs phi, this Fourier coefficient, to be just the unipotent period for this subgroup and this character. So that's the definition of the Fourier coefficient for the pair Fs phi, for the pair S phi, for the Whittaker pair S phi. Okay, so this Whittaker pair S phi, I mean, this little phi, I could think of it by the killing form as some nilpotent element in the Lie algebra itself. This, you can do that canonically. And so then what it means is that what I'm looking at is just a pair that satisfies the relation of a Borel subalgebra of SL2, but not the full SL2. Okay, because you have something that's in the you have something semi-simple and something in the -2 eigenspace. So somehow these Fourier coefficients correspond to an embedding of the Borel of SL2 inside the Lie algebra. Okay. Okay, so anyway, we call this a Fourier coefficient, this Fs phi. And now let me show some examples of this. Okay, very good. So one example, which has been studied a lot, is what we call a neutral Fourier coefficient. And how does that come about? Well, if I have a nilpotent, just a nilpotent phi and G star, then I can actually write down a pair H phi. And how do I do that? Well, first, as I said, by the killing form, phi corresponds to some nilpotent, let's call it F equals F phi in GS -2. And now by Jacobson-Morozov, I can complete it to an SL2 triple in this nilpotent. And so then there I found an H. Okay, and this will satisfy the property that we said. So, but this is a special kind of H that you construct this way. And I will say that it's a neutral H for phi. Yeah, this is Costin's terminology, calls this the neutral element for SL2 triples. I use the terminology of nil positive, neutral, and nil negative. Okay, but this H is a neutral H for phi. And so I will say this is H is neutral for phi, and I'll say FH phi is a neutral coefficient for us. In our situation, it's a neutral Fourier coefficient. And okay, neutral coefficients have been studied by lots of people, but we understood them from the work of David Ginsburg and co-authors, and they are simply called Fourier coefficients in his work. But they are neutral Fourier coefficients for us. Okay. Now, if H and H prime are two neutral elements, then actually H prime is conjugate to H by some G, element G, which stabilizes phi. So neutral coefficients, I mean, the choice is not such a serious choice. Neutral. Also, more generally, if you have a Whittaker pair, so we're looking at, we're advertising studying Fourier coefficients with respect to Whittaker pairs. And so if you have a Whittaker pair, then really what you're changing is you're taking something neutral and adding to it a semi-simple element Z. You're adding to H a Q semi-simple element Z, which centralizes both H and phi. So from the point of view of neutral pairs, we're just adding some semi-simple element in the centralizer of H and phi. Of course, the centralizer of H and phi is a reductive because it centralizes the whole SL2. So in other words, I'm just looking at, in this reductive part, I'm asking, does it have any in the centralizer of this SL2? I'm asking, are there any Q semi-simple elements in this reductive group? And if you have some, then you can add them to your H and you get a more general Whittaker pair. So this should explain, how Whittaker pairs are more general than neutral Fourier coefficients. Of course, okay, so we say that phi is K distinguished if this little f phi is not contained in a proper Levy subalgebra defined over K. Then if you have a K distinguished guy, then of course there are no non-neutral pairs. Because if you have a neutral pair, then there's some Z and that defines a subalgebra. So K distinguished things are rigid from this point of view. You only have neutral coefficients and nothing else. But for others, you will have such things. Okay. So I spoke about neutral coefficients and how they relate to what we are looking at. Now let me look at the other example which motivated this definition. Okay, so you can look at parabolic coefficients. So what are parabolic coefficients? So they are period integrals with respect to a character, let me call it Xi, of the unipotent radical of some parabolic subgroup P equals LU. So we can call this a parabolic Fourier coefficient. Okay, now if Xi is trivial, then this is just called a constant term with respect to this parabolic. If P is a Borel subgroup, so if your group is quasi-split and P is a Borel subgroup, then we call this a Whittaker coefficient, although sometimes this term is reserved when you have a non-degenerate Xi. So P is a Borel, and Xi is non-degenerate, then you might call this a Whittaker coefficient. But okay, we can just call these Whittaker coefficients if we like, for maximal parabolic. All right, and now in string theory, people study parabolic coefficients for maximal parabolics P. That's what shows up. Okay, so now if I have a U and a Xi, it's rather straightforward to find an S which defines the parabolic and such that okay, it's not so difficult to find an S and a phi, so that U is what I was calling NS phi and Xi is what I was calling chi-S phi. It's very easy. So this means that parabolic coefficients are a special case of what we are calling Fourier coefficients. Okay. All right, so our main result, so we're looking at this more general class of coefficients, and our main result involves a quasi-order on Fourier coefficient. So quasi-order is it's like a partial order, except two different things could be greater than or equal to each other. So it becomes a partial order after you mod out by equivalences. Yeah, that's so these Whittaker coefficients, they're sort of locally constant when you vary S. So interesting things happen at discrete points. So anyway, the best way to think about all of this is to talk about a quasi-order. So let me explain this quasi-order, because that's what the result is about. That's how the reduction goes. All right. Now suppose I have two Whittaker pairs. Well, this is supposed to be a curly pi, so I'll call pi for pair. So I'll say pi. So pi is h phi and pi prime is h prime phi prime. If these are Whittaker pairs, then I'm going to say pi is greater. So curly pi is curly greater than or equal to curly pi prime. If first, let me explain it in two basic cases. Then I'll explain the general thing. So one basic case of this quasi-order, one, is if phi prime is equal to phi, h is equal to h prime, and then h and h prime satisfy the following relation. That if I look at stabilizer of phi and I intersect it with the eigenspace greater than or equal to 1 of h, then that's contained in the positive eigenvalues of h minus h prime. Okay, so that's one situation. So really, if I fix phi equals phi prime, then as I explained before, I am really looking at some, I'm looking at the Q split, the Q semi-simple elements in the centralizer of some SL2, and by conjugation, I could, I guess, restrict to just a cartan, a Q split cartan. And in this space, I am imposing a partial order among the possible z's. So this is the partial order. That's one basic case when phi is equal to phi prime. Okay. The other basic case is when h is equal to h prime. Then what I ask is that there is a parabolic subalgebra, P equals L plus N, which is defined over K, with the property that H and F phi prime belong to the Levy, and F phi minus F phi prime belongs to the nil radical. Okay, so those are the two basic cases of the partial order. Very good. And now the general partial order, well, it'll be gamma invariant, but you just piece it together with this. So more generally, I will say that pi is bigger than pi prime. If I have some sequence pi 1 through pi n, where the first guy is pi, the last guy is pi prime, and then I have elements gamma 1 through gamma n in the discrete group gamma, such that each pi I is greater than or equal to gamma I, pi I plus 1 in the senses 1 and 2, either 1 or 2. So it's just a chaining together of these two basic cases in a gamma invariant fashion. So that's the partial order. That's the important partial order for for Whittaker pairs or for their corresponding Fourier coefficients. We will say one is greater than or equal to the other if they're related by this partial order.
Does this, I mean, this is independent of how these things exist? I mean, they don't have to be unique in any way, or in this, you say there exists I mean, could you find, I mean, is it independent of these choices that you make, omega 1 all the way to omega 1, or whatever you call pi, all the way to pi 1?
You're asking, is it a well-defined partial order?
Yes, it's a well-defined partial order. And because you're
So
assuming...
it's not a partial order, it's a quasi-order, but yes, it's a well-defined quasi-order. Yeah, it is well-defined. I mean, I got rid of the choices by throwing in these gammas along the way, basically.
Okay.
Yeah, it's a well-defined quasi-order.
I mean, they look like, I mean, the basic factorization we have for intertwining operators, or I mean, whenever we have a product formula, it's just like this. So is it made to benefit from that, or is there any...
So yeah, Fredun, that's very interesting. I mean, I have not. Okay, so I'm making this definition because that's how things worked out, and from our point of view. But I would be very interested to. I would be very interested to understand some deeper meaning for this partial order.
I mean, in that case, you need a length of the product equal to the product, I mean, sum of the lengths for a...
which product?
Intertwining operators. When you have a factorization like this, when you have a decomposition like this, you have some condition, but I presume, I mean, it should agree with this in some sense. I mean, this is a general way of looking at these things. You just try to write the steps and define it. I just wonder if this is, first of all, well-defined, or if there is any, if you're dealing with all these parabolics, I mean, it doesn't have to be that doesn't have to be a Weyl group element. I mean, it could be going from one unipotent radical to another one when you get this. I mean, it can be given in terms of just a unipotent radicals. Anyway, I'm just trying to see if there's any...
I think these notions are really unrelated.
Okay.
Yeah, I can try and explain later offline.
Okay.
Okay. No, but okay. Okay, but thank you for the question, because it's usually, I guess, when I mean, it's true for everybody that when you do mathematics, you sometimes put on different hats, and when you put on one hat, you're not thinking about something else. And okay, but I will certainly look and see if there's any connection with intertwining operators. As Steve said, I don't see
that it has nothing to do with it, so you may just forget about my question.
No, yeah, but so okay, so in one sense, I see Steve is right, because this is much more general, the framework that we have, but that doesn't mean that it couldn't be related. But I'll try to understand this. But this partial order is kind of crucial for our purposes, as you will just see in a moment. And so it's showing up naturally when one is studying deformations of these. I mean, the whole point is that we took these sort of rigid objects, which are neutral Fourier coefficients, and we allow them to move. Because
you have this parabolic subalgebras. I wondered if that sort of agrees with...
Oh, in the previous, that's one of the examples, though.
I know, but I mean, you will have, in these steps, you will have, different parabolics coming in, and I wonder if you go from one to the other one through that.
So we don't have a parabolic. So maybe
anyway, I shouldn't stop. That's it.
Yeah. No, but maybe it's not such a bad idea. Let's just go back. So we're not really looking at the parabolic defined by S. We're looking at some part of the nil radical, and somewhat carefully chosen part of the nil radical. Let me show you. Yeah. So we're looking at this NS phi.
Mm-hmm.
And this has the eigenspaces bigger than 1. Mm-hmm. Right? The nil radical would be eigenspaces bigger than 0.
Mm-hmm.
If I had some S and I look at the parabolic or the nil radical defined by that, I should take eigenspaces bigger than 0. So what am I doing? I'm actually taking eigenspaces bigger than 1. And from the one eigenspace, I'm only taking, something that's on which phi is trivial.
Okay.
So it's not the full nil radical. The statement I made was that I could choose S so that, let's say, all of the eigenspaces are, the positive eigenspaces are in here. I mean, I can rescale the S so that all the eigenvalues are bigger than 1. Then I get exactly the nil radical of some parabolic.
Okay.
But I mean, it's a little bit subtle because it changes when you rescale S. Right? So yeah, I mean, these things move, and
Yeah,
that's the whole point. I mean,
Don't
nil
worry,
radicals
that's the
are,
question. I mean, that's fine.
nil radicals are rigid. Nevertheless, it may be that at least in that special case there is some connection. So I'll try to take a look. Okay, let me. But thank you for the question.
Sure.
Okay, so this is the partial order, and yeah, so there's this one condition if phi is equal to phi prime, and another condition if h is equal to h prime, and then it's glued together. Okay, and okay, we will also, so when I write 1 and 2, I mean this 1 and 2. I didn't realize this was showing up as a regular 1. Okay, but this 1 and 2 just means this 1 and 2. Okay, so we will also consider this separately, and so we will write h is greater than or equal to sub phi h prime if this happens, and phi is greater than or equal to h phi prime if that happens. So I have a partial order on h's given a phi, I have a partial order on phi is given an h, and it's all kind of strung together in one quasi-order. I mean, they are all quasi-orders, right? Because things that are conjugate by gamma go both ways. All right. So I will say that a pair is Levi-distinguished if h is maximal with respect to phi. So the maximal elements among the possible h's for a phi, I will call them Levi-distinguished. And so, okay, I gave some definition of a fh phi. I don't expect you to kind of, well, basically there's a definition of n as phi and for character. But if you unravel everything, so then you can understand what is this fh phi. So it's a composition of two things. First, you take a parabolic constant term. So I'm describing the maximal elements in this partial order. So first you take a constant term, and then you follow this by computing a k-distinguished coefficient on the Levi subgroup. And since I'm computing a k-distinguished coefficient, there's just only the neutral coefficient to compute, so to speak. So the maximal elements, you can understand them some sort of large. You take a large, you take some constant term such that then you take a k-distinguished coefficient on the Levi. That's what the maximal elements are here. The minimal elements, I didn't write them down, but for any given phi, there is a minimal element, and that is just the neutral coefficient. And so for a fixed phi, Levi distinguished and neutral at the two ends, and then there is a whole zoo of things in between. Well, it's not a zoo. I mean, it's like more like a river because things can flow into each other. Okay, so what's our reduction algorithm? So if I have a pair, S phi bigger than or equal to H phi. So we fix here a phi. I mean, we could also let the phi vary. That's not a big deal, but all of the interesting action happens here already for 1 phi. Then I relate the Fourier coefficient for S phi and H phi. And the point is that I write the Fourier coefficient of H phi in terms of the Fourier coefficient of S phi and plus higher terms. So I will explain what are higher terms. The main point is that the things on the right are higher in the partial order that I described. And this is the this is the thing that you're supposed to do. This is the thing that's useful. Okay, and that's exactly what we do. You can write Fourier coefficients in terms of lower Fourier coefficients, and that's very easy, and it's also completely useless. The hard thing is to go up in the partial order of the quasi-order. I mean, you can write any Fourier coefficient. So the form itself sits at the bottom of the pecking order. And of course, you can write any Fourier coefficient just directly in terms as an integral over the form. That's how they're defined. But that's completely useless. So what you really need is to be able to write a Fourier coefficient in terms of a higher Fourier coefficient. Okay, so that's the algorithm. So there's a main term, and then there are still higher terms. I will explain those. Okay, so let me just explain first what is the main term in this expansion. Okay, so to define the main term, I need to explain 3 Lie algebras. I'll call them U, V, and W. And okay, so first some notation. I have an H and S, they commute, so I can look at simultaneous eigenspaces or more complicated things, and I will write such notation, which should be completely clear what it means. All right, so U is one eigenspace of S intersected with the greater than one eigenspace of H. V is the negative eigenspace of S, sorry, not negative, S less than one eigenspace intersected with GH greater than 1, and W is S less than 1 intersected with GH equals 1. Okay, so, well, these are just subspaces. They are not Lie algebras, but I will think of them as quotients of G by this identification. So if you write it this way, then this is, so whenever you have greater than or equal to, that's a nilpotent. A greater or greater or equal to something positive, that's a nilpotent Lie algebra. So everything that's showing up here is a nilpotent Lie algebra. And and you can check that, these guys are ideals in there. And so when you take the quotient, they become nilpotent Lie algebras also. Okay, so that's the Lie algebra structure in these things by this quotient. And yeah, and now I can then I can define the corresponding groups, because I can lift these nilpotent Lie algebras to nilpotent groups. And so U and V will be the groups of Adele points, but this omega. So I'm calling this UV, and I'm calling this omega rather than W, because it's actually discrete. So it's W of K, but not W of A. So U and V are adelic, and omega is discrete. Okay. Then okay, yeah, so okay, I'm repeating myself. Note that omega is discrete, because it's just a discrete Lie algebra. Okay, so now I define for a function f with suitable invariance property that will be satisfied by this Fourier coefficient. So I define m as h of f. Well, first I sum over omega, and then I integrate over v, and then I integrate over this coset for u of f, w, v, u, g, du, dv. So that's the main term in this expansion. It's two integrals and a discrete sum. More appropriately, it's a compact integral, it's an adelic integral, and a discrete sum. So the bracket u, that's a compact integral. Okay, those are the parts. This is how you put them together to get the main term. Now, what about the higher? Yeah, go ahead. Somebody has a question.
Yeah, so I'm familiar with seeing similar formulas with the exchange of roots technique. So that's what you would get. That's the analog or the generalization of that.
Yes, absolutely. I was going to explain in a moment this point. Yeah, but you're absolutely right. So we developed Dima Gurevich and Raul Gomez and I. We developed our own techniques in the generality of Whittaker pairs, but they have of course many points of contact with this earlier idea of root exchange. That's absolutely correct. Yeah, there's no doubt about that. Okay, but here this is the main term that you get. Okay, and now the higher terms in this formula are similar to 5, and you can read them in the paper. I don't want to write them down. I will explain how they arise, and the point is that they are similar to 5, but they involve Fourier coefficients h prime phi prime, where h prime phi prime is bigger than h phi, but phi prime is not in the gamma orbit of phi. So they really come from higher orbits, apart from the main term. Okay. And this means in particular that the closure of the GC orbit of phi prime, even that properly contains the GC orbit of phi. So it's higher not just in the K sense, but also in the stronger sense of complex orbits, which is good. The higher, the better. Okay, and so by iterating this procedure, so I explained how to express h phi in terms of s phi, but I could repeat the procedure for things that show up. And then what we deduce is that any Fourier coefficient can be expressed in terms of Levi-distinguished Fourier coefficients, which are bigger in the partial order. So Levi-distinguished, remember, that's a very, it's kind of easy to understand. It's a constant term followed by a k-distinguished coefficient. Those are the maximal things. So in this procedure, you can write anything in terms of those, in terms of Levi-distinguished maximal elements dominating your element. And the form itself can be just expressed in terms of Levi-distinguished. Because the form, yeah, since the form is kind of at the bottom of the hierarchy of Fourier coefficients, you can express it. Any Levi-distinguished coefficient could show up and potentially show up in its expansion. But if you have a higher Fourier coefficient, not every Levi-distinguished coefficient will show up in its expansion. Okay, so now if you have cuspidal form, which means that there are no all constant terms are 0, then you can just express it in terms of k distinguished, because that's the only thing you're allowed to do. Okay, now when I'm doing this expansion, so there is an important special case for which the higher terms vanish. Let me just state that. I'm not going to describe all the higher terms. I mean, you can look at the paper. And, well, I'll say something about the proof. Yeah, I should just try to explain easy things. I think that's important, not the hard things. Okay. So let me just define some partial order on nilpotent elements. So I will write psi is bigger than phi if okay, so it's some refinement of this partial order that I had. So psi should be bigger sub h phi for some h, but I don't want psi to be in the gamma orbit of phi. So this is okay. It looks kind of yeah, somewhat delicate definition, but it's the right one. So I had some previous partial order. I just say that two things are related. If I can find some witness h, which says that psi is bigger than phi, first of all, and but also psi is not really, doesn't live in the same house as phi. Okay. So then, all right. So with this definition, I will say that some phi is in the Whittaker support of eta if some Fourier coefficient with phi is not 0 for some s, but for higher things, all Fourier coefficients vanish. Then I'll say that this is in the Whittaker support. And so suppose I have, now this is about the form. So suppose phi is in the Whittaker support of the form, and I have s phi bigger than h phi, then the Fourier coefficient h phi is just equal to the main term applied to this s phi. So this is yeah. So this algorithm and is yeah. So that's a special case of this algorithm where you don't have to know the higher terms because they all vanish. Okay. So then maybe so I explained everything for this term. I'm just telling you there's no higher term. So in this condition, there's a formula that I gave you in some earlier page. Otherwise, there's more stuff. Okay, so let me explain to you the proof of this. All right, so what happens is that in order to, as always, with some proof, when you start trying to prove something, you maybe need to change the language or you need to generalize some notion. And so what we need is this idea of quasi-Fourier coefficients. So what are quasi-Fourier coefficients? Well, they're defined in a completely analogous manner to the Fourier coefficients, but they use Whittaker triples. So what's a Whittaker triple? So it's an s phi and phi prime, where s and phi are just a Whittaker pair, but phi prime is something in the eigenspace bigger than -2. So this gives me just a tiny bit more flexibility than Whittaker pairs. So I still define n as phi, and this phi plus phi prime as before. And this phi plus phi prime will define a character of n as phi. Because when you bracket, yeah, when you bracket, you move to when you bracket n as phi, you move to some eigenspace bigger than 2. Well, unless you were in the eigenspace 2, but phi prime will for sure, unless you were unless both things were in eigenspace 1, but phi prime for sure will vanish on the bracket because it's in space -2 and bigger. So therefore, phi plus phi prime will define a character of n as phi. So n as phi was okay. I defined it, and such a phi prime you can add to phi and get a different character, and then you can compute the unipotent period with respect to that. Okay. So this is this is what is a quasi-Fourier coefficient. And okay, so now how do we study? Now let me go back to the problem. So I want to relate S phi and H phi. Well, I do the simplest possible thing, namely I connect them by a one-parameter family. So I have S and H. Well, I just look at H sub t, which is H plus t times S minus H, and I let t vary between 0 and 1. Okay, well, yeah, strictly speaking, I should only let it vary over the rational numbers. That's fine. That's pretty good. This is good enough. So I just let t vary on this interval 0 and 1. Because things are Q semi-simple, so I can still talk about the positivity of the eigenvalues and so on. And it will just depend on rational things, but never mind. This is the whole point, that you can flow S to H, or in fact, in this case, H to S. And now we can study this FHT phi by a global version of the techniques of GGS1, GGS2, which are also in various cases in the work of David Ginsburg and co-authors. And the point is that the Fourier coefficients, the structure is locally constant along this. Nothing changes because things are defined by eigenvalues, and you have to watch out as you're varying the parameter. Do some eigenvalues become 1, or they become bigger than 1, become less than 1? Do they become 2? Do they become less than 2? Do they become more than 2? So this is the only thing that you have to keep track of, and this happens at some sort of discrete set of points. So what happens is that a certain critical t, as you move from H to S, at some critical t, at some critical values of this parameter t, additional coefficients appear. In other words, you're just led to additional coefficients, and these are in general quasi-Fourier coefficients. They're not necessarily Fourier coefficients; they're quasi-Fourier coefficients. Oh, you can recognize them as such if you're looking. I mean, you have a sort of a mess, but you kind of recognize that this mess is really should be called a quasi-Fourier coefficient, and it's just the same as a Fourier coefficient with another moving part. Okay, now these so now you restart. So for each quasi-Fourier coefficient, you restart the procedure. You don't want to stop at quasi-Fourier coefficients. You want to deform them to Fourier coefficient. So how do you do that? Well, remember the main line was going in a straight line from H to S. Now, at some point, I have a quasi-Fourier coefficient that's associated to a higher orbit. Where do I go? Well, on this space where I have a higher orbit, I have a neutral point, which is sort of like the 0. So I just draw a straight line from 0 to this quasi-Fourier coefficient, and I keep going away from the neutral point. So it's like getting out of Dodge. Okay. So then when you go this way with these quasi-Fourier coefficients, okay, there might be critical points which generate even higher quasi-Fourier coefficients, but each of those you can resolve. And every main line for these quasi-Fourier coefficients will eventually get you to a Fourier coefficient. And at all stages, the point is that you get higher and higher orbits. So eventually you will run out of steam. Okay, so you write these quasi-guys in terms of still higher Fourier coefficients by deforming along a straight line away from a neutral element. All right, so then the final result that you get the main term for S phi together with these higher Fourier coefficients. And that's the reduction element. Okay, so I think that's all I have to say.
Thank you very much. Questions, please.
So,
Yeah, can I have a question? So, is there a definite direction that so where we're going? Like, so for example, if I was given like some neutral pair, and so it seems to me that like I'm sorry, like if I just have another arbitrary like a Whittaker pair, and is it possible to compare like the Fourier coefficients like so for arbitrary two Whittaker pairs, or like
I mean, so, okay, so you can always go down. That's easy. So you could go down and go up.
so
Yes. And
yep.
then, okay, but then this is kind of lossy. If I have any Fourier coefficient, I can express, I mean, the point is that I can express, okay, the form itself sits at the bottom, right? So you can write the form, so you have two coefficients. You could write the form in terms of one coefficient. That's kind of easy. And then you can go up and write the other coefficient. You can try to get a formula. So, I mean, so going up is hard, going down is easy. You can, okay, let me not try to say this. Going up is hard, going down is easy. You can always go down and go up. But then you lose information. Your expression will have lots and lots of terms. And in this business, complexity is the enemy. The more complicated your expression, the less information it has. So, right. First of all, you have to know which way is up, and you want to know that beautiful results or useful results are found by climbing up the mountain.
And also like so if I'm comparing two Whittaker pair, the Fourier coefficient of two Whittaker pairs, so where the nilpotent element like belongs to different orbits, because like if they belong to the same orbit, it seems to me that it's like quite straightforward that you're just there's a plane, there's a affine space where you can just like move further away to the
there's a straight line path, right?
Yeah, but so if they
okay,
belong to different orbit.
So the thing is, you can write any coefficient in terms of any coefficient. The question is, how should you do it, and then how do you control what shows up? And so if you have just two pairs, you can, I mean, the region is star-shaped. I mean, you can make a choice. I don't think we looked at this carefully. You could choose that I can take something. It makes sense to go down the shortest valley and then go up.
So like if you're going to the higher orbits, is there a preferred direction to choose?
We didn't think about
like transversal,
but it should be. It should be. possible. I guess you should maybe, yeah, I don't know. Maybe you should first go to the Levi-distinguished. Okay, no, I haven't thought about that too much. Maybe there is a way. I mean, okay, let's discuss that separately.
Yeah, sure. Thanks. Thank you.
Yeah, let's discuss that separately.
So I have a question.
Yes, Eyal.
The techniques. So in your previous was GGS1, GGS2. So the the Archimedean part was completely new, and the p-adic case was sometimes a really reformulation of known techniques, right? And they didn't consider central extensions. So what happens now?
Well, I think we realized that we could work with central extensions, that there was no restriction in what we're doing. That's all that happened.
But you don't have any specific motivation for doing so, right?
Well, I mean, a secret motivation.
No, a specific.
Yeah, no, there is a secret motivation, which is kind of far. So it's another hat that I wear from time to time about metaplectic Whittaker functions.
Okay, but don't tell me the secret.
No. It's not. No. It's secret only because I'm not wearing that hat right now. Maybe I'll wear this hat in Sol's talk later this month. But certainly, I mean, Whittaker functions for metaplectic covers are important or fun things to look at. And so, why develop a theory for? Well, if the theory doesn't need that you have anything about the group being linear, so why not just work in that generality? Yeah. I mean, right. So, yeah.
So is this the notion of the quasi-order can be defined for local field?
Oh, can it be defined for a local field? Good point. I think so. I mean, the definition.
You use rational point.
Yeah, but that's just because I want to work for a number field. But yeah, sure, no problem. I think. Levi, let me just check. No, I'm too far.
You use gamma, use gamma.
Yeah, gamma conjugation. Yeah, probably K conjugation. I mean, the K would be the compact group or something.
You replace gamma by K, or?
I think so. I mean, so it depends on how flexible. I mean, how delicate we want this notion to be. But there should be an appropriate notion of conjugacy so that the class of coefficients you're considering is unchanged, right?
Mm-hmm.
But the main idea, I mean, 1 and 2 are the main things, and then the conjugacy is whatever is appropriate.
Okay.
I mean, there's no problem with this definition. It's all about yeah.
Yeah, 1 and 2 is okay.
Yeah, exactly. And then you chain it together.
So over local field, number 2 becomes, I think, equivalent to phi prime lying in the closure of the orbit of phi under the centralizer of H.
Yeah, that's true. That is true.
Yeah. This is something we don't have of a number field, because closure in what topology? I mean, it will imply that it lies in the closure in any local topology,
yes,
but
yes,
I'm not sure it will be equivalent to this.
Yeah.
But
closure of the centralizer.
A closure of the orbit of phi under the centralizer of the semi-simple element H.
Yeah.
Well, it's all based on local theory, right? So of course it works there.
That's right. That's a good point, Timo.
You not never try this?
Is the what?
Do you have anything write down for local? Or?
Yes, so I think you know our local paper with Raul Gomez. There are two of them. This talk is more similar to the support paper, Whittaker supports of representations.
Yeah,
which is in some sense continuation of your paper with Baying and Gordon.
Yes.
So we wanted to understand your paper in terms of our techniques, and also to provide an Archimedean case. Now, this work over adels, first it's automorphic, but second we wanted to explicate the more abstract statements that we had in the local case.
Yeah. And third, we wanted to get a formula which we can apply to maybe study some physics, but that's coming.
Yeah, yes, and it's providing much shorter formula. If we would just read and do whatever is written there, it would be some huge incomprehensible formula. So this is more general, and indeed one can go back to the local fields and obtain a local analog of this.
Yes.
It would be something new. It's not so difficult to obtain it, so we wouldn't do this, but it would be something new.
Unless there were some goal. So if there were some goal.
Yes, if there's some goal, we can write that.
The goal
so the paper, Dima, so the paper you're talking is this GGS1, GGS2?
Yes.
Yeah, GGS2, right?
Okay.
GGS2.
Okay, good.
So for the
it is to appear in Annals of Institute Fourier, but I guess the production there was really slowed down by the pandemics. We are not getting, but anyway, it's in the archives.
So I have one more question regarding the elements. Here it's on the slide, gamma 1 up to gamma n minus 1. There's no notion of a minimal number of elements, right? I mean, it can be any n.
Oh no, yeah, this is just a chain. You could take, so it's just you're generating, if you have any relation, you can generate, you can generate a quasi-order out of it. I mean, this is like really, really stupid. So this is all it is. There's something to check that this is actually, but there's not so much to check, right? If you just have it, so the point is So the point is that if you have, so this is what I'm doing is essentially I'm taking the gamma invariant transitive closure of 1 and 2. So conditions 1 and 2 are the main. And then I'm constructing from that. Well, first I'm making a gamma invariant so that, and then I'm taking the transitive closure. And I'm doing it in one fell swoop, and perhaps that's causing some confusion. But it's not, all of the action already happened in 1 and 2, in those two cases.
I have one more question about this order.
Yes, do you? Yeah.
So you take the consecutive ones of the basic. This looks like the composition of your coefficient, right?
Oh, if I do no. So the coefficients.
You just expansion
or consecutive with respect to 1.
Yeah, you have like
with the same phi.
You try to expand it, right? So
yeah, I think that's what we're doing. We're doing an expansion. So the theorem proves an expansion.
So expansion means that is the composition of the two coefficients, right? Right. You take a coefficient and then you take a coefficient again, and then you try to expand it. Is this true?
I'm not sure I understand.
Is it like step 1, like 2 things can happen? Like one is that you do.
So you take a Fourier coefficient, and then this automorphic form from the big group now become automorphic form in the centralizer.
Ah,
Yeah.
Then you want to do it further Fourier coefficient. And when you do the further Fourier coefficient, you want to write it as a Fourier coefficient of original big group. So this has something to do with?
so I don't completely understand. Are you talking about integration by stages or something?
No,
Fourier coefficient itself. You take an iterated integral.
No, you take an integral. Yeah, I sort of, right? So you take an Fourier coefficient.
Yes.
And then this automorphic form becomes automorphic form, automorphic function is a centralizer, right?
Yes. And then you take a Fourier coefficient on the centralizer.
Yeah.
So, Levi, I guess I don't think about it that way, but
You didn't think of, I
No,
thought
no.
that your expansion, you're like higher terms is a kind of this nature, right?
Okay, so it's not a question about the order, then it's a question about the algorithm.
Yeah, the algorithm is something.
Yeah.
Try to write Fourier coefficient and then Fourier coefficient of the centralizer, and then you just try to produce the Fourier coefficient of the big group, original group.
Maybe you're right.
Right. So this is what you're doing, right? No.
Yes, I guess we could think of it that way, perhaps. I mean, I guess. Right, I'm not 100% sure, but very happy to discuss maybe afterwards. Maybe I can show you.
What do you think?
So my problem is that when you say centralizer, it means centralizer of the pair. So it should centralize both H and phi.
Yeah.
And so we are the further integration is on some smaller group, which is not exactly of this kind, that some semi-simple, it's not just eigenvalues of some semi-simple element, but it also should centralize some nilpotent element. So maybe in some cases we can arrange the semi-simple element to make sure that it centralizes the nilpotent element. Say it's lowest weight vector, something like this. There's only all the vectors of this small weight are lowest weight vectors, but I think only in some cases.
For the case of the Levi-distinguished guys, that's exactly what the Fourier coefficient is exactly like this. That you take a constant.
You take a constant term on the radical, right?
Yes, and then
you take the Fourier coefficient. So this is a kind of composition.
Absolutely.
So that you become.
But that's only one case where you have such a structure.
Yes, and that's because the original phi is 0, so you have no problem centralizing it.
Exactly.
Yes. Yeah.
Exactly. But the more general Fourier coefficient is not of this nature, do you?
Well, you have more terms, probably.
Okay, no. The more terms is when you relate, when you have. Okay, so the more terms is a story of two Fourier coefficients.
Yeah.
Okay, so I have one Fourier coefficient, and I mean it's something about pairs of pairs. Right. I have one guy and I have another guy up on the mountain. And I want to express myself in terms of this higher guy on the mountain.
Okay.
Then I need main term and extra terms. But if it's just one Fourier coefficient, it's given by some formula. And that's all. I mean,
so another thing is when you introduce this pair, you know, the original guy you call the neutral Fourier coefficient.
Yes.
Right.
Yes.
So this means that in this Fourier coefficient you have the extra things. This is really the essential. This Z, right?
Z is 0 for the neutral case.
Yeah, neutral cases, but in general, this Z plays a substantial role here, right?
Absolutely, absolutely. So what I'm saying is that, okay, let's fix some phi. So there's a neutral guy. No, let's actually fix an H and a phi.
Mm-hmm.
Okay, so the neutral guy, and so then all of these are just controlled by this Z.
Yeah,
Okay, so Z equals 0.
that's a neutral,
That's the neutral.
right?
And Z equals infinity in some appropriate sense, or in sort of all directions, is Levi-distinguished.
Uh-huh.
So one thing, I mean, what you might want to do is you might actually want to take a neutral coefficient and write it in terms of a Levi-distinguished coefficient. Maybe that's where you're headed.
Mm-hmm.
So my algorithm just says go to anything. But you could say, well, I want to just express this Fourier coefficient, this neutral Fourier coefficient at 0 in terms of something Levi-distinguished. Namely, I want to express it in terms of the procedure of taking a constant term and then taking something distinguished.
Okay.
Or if it's cuspidal, so suppose you started with something cuspidal, then there's no constant term, so you want to write it in terms of, I mean, I think I explained, yeah, these three things. So so part one, it says that you can actually express it in terms of Levi-distinguished. And how would you do this? Well, you choose to go to something Levi-distinguished, and along the way you get other Fourier coefficients, and then you push them also to some Levi-distinguished things.
Right.
In this way, everything becomes Levi-distinguished.
Yeah. So without Z, you cannot do this.
No. That's the point of the Z. It gives you sort of, I don't know, it's a rope. You climb the mountain along the rope.
Right. Yeah, that's very good. Very good. Thank you. Yeah, very good.
You're welcome. You're welcome.
Yeah.
Can you see my hands and so on when I'm talking?
Yeah, sure.
Yeah.
Oh, okay. I wasn't sure what you're seeing.
Yeah. So
I was trying to explain things with my hand.
Your talk's very lively.
Okay. Fine. Very good.
All right. So are there any more questions? Then thank you very much again.
All right. Thank you. Bye-bye.
Bye.
So next week, we don't have any talks due to Remembrance Day of fallen soldiers. And then in April 21, we will have a talk by Manish Patnaik that could be somewhat related.
What is he talking about? He has a title?
Not yet, but just knowing Manish could be.
Yeah, but is it metaplectic, his talk?
So I don't know. I will ask him to send the title.
Okay. All right. Okay. Bye, everybody.
Bye.